Hello guys, welcome to the Innovation Lab. So we recently found a way to modify these DC to DC boost converters to allow us to increase the output power that we're getting out of these converters, and we're going to show you guys everything that we have done in this video. Alright guys, before we get started, I would like to give you guys an update regarding our 5000 watt DC to DC boost converter design. We have actually been able to build a prototype board and we received it. I'm highly impressed by the work they did. And yeah, we're going to be testing this board, assembling all the parts, and in the end, we'll be able to test it. So my plan is to actually show the progress that we have made on this design in our next video. And if you would like to see that, make sure you subscribe to the Innovation Lab. Also, in the near future, we're going to be making a few product review videos to look at the performance of a couple lab equipment that we just bought. The first one is going to be a digital soldering microscope that I bought to help me with my SMD soldering for boards like this. And the second product is actually kind of a fancy soldering iron, a very nice and neat design. I was really amazed when I saw that and I wanted to give it a try. So again, if you guys would like to see all these videos, don't forget to subscribe to the Innovation Lab so you get notified as we are releasing those videos. All right, my friends, now let's get started. Alright guys, for the testing, let's go ahead and look at what we have on our test setup. That way, as we're going through the video, you guys will fully understand the setup and what you're looking at. Alright, as you guys can see here, we have our collection of 4 server power supplies. The goal is to drive this test up to 48 volts, and each of these server power supplies can give us up to 750 watts of power. So that gives us a possible power supply rack of about 3000 watts. All right, so over here we have our input current clamp and our input voltmeter here. On the output side, we have our output DMM here and our output current clamp here. So as we go through the testing, we're going to be showing you guys the efficiency numbers at the different input voltage levels, also at the different output loads. All right, and over here we have our circuit breaker, and obviously we have our load here. Our load should be able to go up to about 2000 watts the way we have them configured. All right guys, for the 48 volt test, what we did was essentially to apply a load at the output of the converter, and we slowly increased the output to about 67.5 volts, and the load was pulling about 27.86 amps at the output of the converter. And this means that at the input we got 48 volts going in and 40.5 amps going into the converter. Also, when we do the math, what we see was that we have an input power of 1952.1 watts going into the converter and an output power of 1869.4 watts coming out of the converter going to our load. And our efficiency given the input and output was about 95.7, approximately 96%. And also that means that we were only losing about 82.7 watts as power losses going through the converter. All right, for the 36 volt test, we basically repeated the same steps, the same process. We increased the output voltage of the converter until we got to about 75.5 volts, and the converter was supplying about 20.74 amps to our load. So when we do the math, we saw that we have an overall input power of 1666.4 watts going into the converter and an output power of 1565.9 watts coming out of the converter going into our load. And that gave us an overall efficiency of about 94%, which I think is also awesome, and a power loss of 101.4 watts. Alright guys, for the 24 volt test, we were able to get to an output voltage of 64.9 volts at a supplied current of 17.79 amps. And when we do the math, we'll see that we were able to supply an input power of 1270 watts going into the converter, an output power of 1154.6 watts going to our load. So overall, looking at our efficiency, we got about 91% going through the converter at a power loss of 115.4 watts. Alright guys, and finally for the 12 volt test, we were able to get to an output voltage level of 44.36 volts and a delivered output current of 12.09 amps. And as you guys can see here, we were able to actually pull about 60.86 amps into the converter, and this is really amazing. So when we do the math on all of this, overall we have an input power of 724.2 watts going into the converter, an output power of 536.3 watts going out of the converter into our load, and this gave us an efficiency of 74% and a total power loss of about 188.2 watts. Alright guys, so my observation with the 12 volt test is that given the high input current and also the much dissipation that we are seeing through the power losses, these converters have like a very small heat sink, so it's very hard to stabilize the system at that high input current. And this also goes to demonstrate the reason why it's never really advisable to drive these converters at a low input voltage, because the lower your input voltage, the more the power you're going to dissipate as losses, and also the lower the conversion efficiency that you're going to get out of your converters. Alright guys, I hope you guys are having fun so far, and if the testing was all you wanted to see out of this video, I believe you should be good to go. But if you really want to see all the changes, the updates, the modifications that we have made to this converter to be able to accomplish this, I'll highly encourage you to keep watching. Alright my friends, let's jump right into it. Alright guys, so what I've done is to put together a kind of an interactive presentation to show you guys all the sections that we modified, and so you guys can see everything clearly. Alright, so what you guys are looking at here is the kind of the fundamental building block of a constant voltage, constant current DC to DC boost converter or buck converter. So you have the PWM controller here, which is the TL494. You have the input power, then you have your output power section, the load, current feedback loop, voltage feedback loop. All right, so what we have done is to kind of focus on a few key areas. So we basically found a way to adjust the switching frequency of the converter. And the reason we did that was because we redesigned the power inductor. So we needed to kind of tune that switching frequency to optimize the performance of the power inductor. Also, the redesign of the power inductor allowed us to increase the saturation current of the power inductor. Alright, so the final section of what we did was we realized that on these converters, there is a provision to double the output current shunt on the converter, and we kind of took advantage of that. Alright guys, for the switching frequency adjustment, all I basically did was to replace the resistor value here on pin 6, as you guys can see here, which is the RT pin of the TL494. I replaced it with a potentiometer, kind of a resistor network, such that the potentiometer will help me trim the frequency up and down. So what I'm going to do is to run this a kind of an animation to show you guys exactly what I did. So this is a TL494 and it has a maximum switching frequency of 300 kilohertz. So the dot here is kind of shows you where pin 1 is on the board. So if you're looking at the DC to DC boost converter that we modified, so if you look at the set of pins that are inside the board, you guys can kind of see where pin 1 is, and you can figure out where pin 6 is from there. Alright, and this is the formula for calculating the switching frequency. Essentially 1 divided by a product of RT multiplied by CT. Alright, so this is what I was saying. I basically used 200 ohms, one connected to pin 6 and one connected to ground, and I added 100K trim potentiometer. That is what's going to allow us to vary the frequency there. So as you guys can see in the formula, if you vary the resistance value, the frequency is going to change. And our frequency goal was to stay somewhere between 10 kilohertz and 60 kilohertz. Alright guys, to keep things simple for the current feedback, the only thing that we did was to double the output current sense shunt that we have on the converter, as you guys can see here. So and I realized this looking at the output section of the converter while I was designing my new converter, that the manufacturer had actually made provision for this second shunt here. I don't know if their plan was to be able to increase the capacity of the converter in the future, but that's what I'm using it for. So basically, if you go by Ohm's law, if you double the shunts here, let's assume that the first one is like 0.1 ohms. And if you double it now, you have 0.05 ohms. So essentially, if we have these resistors connected in parallel, the resistance drops. That means if you go by Ohm's law, now you need double the current at the output to be able to set the same exact voltage that tells the TL494 how much current that the load is drawing. So that's the whole goal of this design, is to fool the converter to say, okay, now hold the PWM on state of the duty cycle, don't shift it until we get more load on the system. But again, full disclosure, to be fully honest, I realized that as much as this makes sense in calculation, I saw that the original converter design, they had added an output overcurrent protection. This means that this portion of the modification may not really help us a lot to double the output current going out of the converter, but everything else that we did with the switching frequency and redesigning the power inductor actually does help us to increase the input current limit that is coming into the converter. Alright guys, for the power inductor design, so we conducted a ton of research and a lot of calculations to see how we can design the power inductor to optimize the efficiency of the converter and also increase the saturation current of the converter. So some of the key variables or parameters that we looked at included things like skin effect or skin depth of the copper gauges that we're going to use. We looked at the overall inductance, and that was driven by our calculation of critical inductance. We considered the saturation current, and that was why we kind of stacked those cores to be able to make sure that the saturation current of the cores that we're using will not be a problem. And actually for this design, the core material that we're using is the manganese zinc ferrite toroidal core, and we also looked at flux density, magnetic path length, and many other things that we considered that I'm not sure that you guys will be interested for this level of detail. Alright guys, so one of the things I wanted to show you guys here is that as you guys look at the power inductor, you guys will kind of see that instead of using a collection of single core wire gauges, we actually used a bunch of laminated smaller cores and we twisted them, and the reason for that is because of a concept known as skin effect or skin depth. So skin effect in a nutshell kind of describes how copper wires or conductors behave in a high frequency environment or a high frequency power with respect to how they would behave in a DC power. So what you're looking at here, let's take for example that this is a big gauge copper wire, and in a DC conduction mode, as you guys can see, the entire core of the wire, the entire cross section of the wire will conduct 100%. But if you subject the same thick gauge to high frequency power transmission, so what skin effect shows us is that electrons will tend to flow only at a certain depth from the diameter of the, or from the center of the wire gauge. So the thicker the wire, the more of this effect that you're going to see. So, and this is more prevalent at high frequencies. And this is the reason why we have to pay very close attention to the skin depth of the wires that we're using. So looking at the original inductor design that they have for these converters, you can kind of see that, I don't know, maybe to save costs, they didn't pay much attention to this. And that would make a lot of sense because the designs, the way I have them, is quite expensive to build the converters. The inductors are hard to build, and also you have to spend a lot of time winding those copper wires, then twisting them in the end. So yeah, so as you guys can see here, so this is kind of the twisted version. So now I'm using gauge 22 for our inductor design. So you see, I think I used about the collection of about 50 strands of the gauge 22, and I twisted them real tightly so that they will fit through the inductor core that we're using. So, and the impact is, as you guys can see, so gauge 22 actually gives us 100% skin depth at 42 kilohertz. So what that means is at 42 kilohertz or below, you're going to be able to get all your power going through the cables, no losses as a result of skin depth or skin effect. And this is amazing. So if you guys are seeing the improved efficiency numbers, yeah, part of it comes from using the stranded inductor wire strategy that we're showing you guys here. Yeah, so that's it in a nutshell. So what I did for the design is to stack a couple of the toroidal cores to make sure that we don't run into a problem with saturation current. Also, stacking the cores helped me get closer to the inductance value that I was aiming at. For this converter, I realized that your target should really be somewhere between 30 to 100 microhenries for your inductor design, and that seems to work very well. Yeah, so that's pretty much what we did in a nutshell. So inductor design by itself is a very intricate process. This could actually be a series of videos if people will be interested. It's not going to be one video, so I'm doing the best I can to explain what we have done here. So you guys can kind of look at my inductor design and let it guide you. I will leave all the part numbers, the cores that I'm using from eBay, and you guys can also go find those cores. And if you're not going to be able to make it in the future, I'll see if I can make some of those cores, some of those inductors available to you guys, and you guys should be able to access them through our website. All right, guys, that's pretty much what we did for the inductor design. And you guys let me know if you have any question. Leave us your questions in the comments down below. Alright guys, that's it for this video. I am glad you guys were able to make it to this point. As you guys have seen during the testing, we were able to exceed 1800 watts of output power at an input voltage level of 48 volts, and we did that while maintaining an efficiency of about 96%. If you ask me, I would say that's quite impressive. Alright guys, so looking at all the tests that we have conducted, we can kind of say that the 48 volt test could be considered as the best test condition, but actually it could have been better. I believe that we could have gotten more power out of the system if we used an input voltage of 60 volts, but I didn't quite have a 60 volt power supply here, so the best we could do was the 48 volts. Also, one of the tests that we conducted was to subject the converter to an input voltage level of 12 volts. On the other hand, this could be seen as the worst test condition because these converters do not do well at very low input voltage. But regardless, we were able to get an input current of about 60 amps going to the unit at 12 volts, and we got an output power overall of above 500 watts. If you ask me, I would say that's quite impressive. The only downside to using the 12 volts is that your measured efficiency is not going to be that great. As you guys have seen during the testing, we were only able to get to about 74%. Alright guys, we have shown you guys everything that we have done, and my goal was to really share this amazing experiment with you guys. And at this point, it's really up to you guys what you decide to do or not do with the design concept. One thing I recommend is that it's always good to play with the switching frequency of the converter, but try not to go too low. As you guys saw in my video, I wasn't going below 30 kilohertz. And also you can choose to be a bit more conservative with your power inductor design. I don't think you have to have it this big as I have it here. Actually, I made it this big because my plan is to reuse this power inductor for my 5000 watt DC to DC boost converter design that I'm working on. Yeah. Alright guys, that's it for this video, and I hope you guys had fun. If you have any question, leave me comments down below and I will do my best to answer your questions. And yeah, and if you're new to our channel, don't forget to subscribe to the Innovation Lab to see more content like this in the future. All right, my friends, thanks for watching, and I'll see you guys in the next video.